Can you see my white page? Yes or no?
Yes, sir.
Okay, okay. Take. Okay, so let us first recall. So what we are doing in the last class was that f is a continuous C2 CRN. You know what is the meaning of that? A C2 function which compacts up, and phi x is about the fundamental solution for the Laplacian. Okay, so that means Laplacian of phi of x equal to 0 when x not equal to 0. Of course, there is a problem at x equal to 0. That we don't have to bother now. So phi x is given by minus 1 by 2 for x not equal to 0. For x not equal to 0. Phi x is given minus 1 by 2 pi log of mod x if n equal to 2, and the constant mod x to the power 2 minus n if n greater than equal to 3. And I have said already that why this constant come into play. This is something related to some Dirac delta that you will learn later. And so for if you don't like this constant, you just write down c1 log x and c2 cn, because it's of course the constant should depend on n. So the cn mod x to the power 2 minus n. That's all enough. That is enough. Okay. Okay. So and given f to be a given function, then what we did, can anyone recall what we have done? Huh? Yes.
We have proved that F convolution with this
Phi define.
solution.
First of all, you define a function u, which is defined as phi convolution of f, which is same as f convolution with phi. Okay. Then this function u is in C2 of Rn. First of all, and it solves minus Laplacian of u is equal to fx for all x in Rn. Okay. So two parts. So if you take any function f, okay, which is a C2 and with compact support, and phi is this fundamental solution. If you convolve, you define a new function u, then u is of course a C2 function, and u satisfies this equation. This is most important, that u satisfies the equation minus Laplacian of u equal to fx. So what we did, if you remember, you first define u of fx is nothing but phi of x minus y f of y dy. This is your R. This is the definition of the convolution. Okay, and you write down for n equal to 2 and for n greater than equal to 3. Let us just consider n greater than equal to 3. Then at that time, this will be n into n minus 2 into alpha n Rn out of x minus y 2 minus n fy dy. And we compute, somehow we compute Laplacian of ux. We know how to do this and all those things. That Laplacian of u, and we compute and we use the integration by parts many times to solve that, this Laplacian minus Laplacian of u equal to fx. Okay. Just recall one step which I will need again this for this class also. So which term gives us this? If you remember well the proof, there was a term called b. I called it b, which is nothing but del b 0 epsilon del phi. You know what is the meaning of del phi by del nu y f of x minus y d of sigma y. Of course, this integral is on the boundary of the ball of radius epsilon centered at origin. Okay. Okay. Now you tell me, letting epsilon tending to 0, where b will tend. Anyone? Anyone? If you remember, recall the steps of the proof of that theorem, this theorem, then that is the most important step. From where we get? Can you remember, anyone? If you don't remember, I can do it again. B tending to fx. Okay. So if you don't remember, just you do this. Del nu y fx minus fx plus f of x minus y d sigma y. So you take this first term fx del b 0 epsilon del phi by del nu y plus del b 0 epsilon f of x minus y minus of fx d of sigma y. Okay, and this as f is into, sorry, there is multiply with d phi by d nu. So as f is a continuous function, as epsilon tending to 0, using the continuity, this integral will go to 0 and this integral will go to 1 and this is fx. I have done it important. This will be fx. Okay, these I will be using for this class also. Okay, so what we have done is that if f is given to be some C2 CRN, we have proved a representation formula that if you convolve phi convolve with f, we obtain u is the solution of the equation minus Laplacian of u equal to fn in Rn. Okay, so this is one. I am not saying that all the solutions will be of this form, but if you are given that minus Laplacian of u equal to f and f is given to be a C2 CRn function, then one can compute easily that then one solution of this PDE is given by phi convolution f. Of course, not all the solutions, but at least one solution will be given by this. Okay. Okay. This is for Rn. Now we want to study this problem in a bounded domain. Okay. So what for the case? Now we shall want to study. So this is the explicit solution of the PDE minus Laplacian of equal to f in Rn. So one explicit solution is phi convolution f. Okay. Now we want to study the same way, the same type of same type of idea can be done in Rn or omega. So now we shall want to study the same question for a bounded domain. Okay, there should be something real, because if you see the proof, when I'm doing the convolution is very nice in Rn. You know why? Because x minus y, that should lie in the in our domain Rn, right? Otherwise we can't do the convolution, right? You know that f of x minus, because this x minus y type of term comes, and why f of x minus y will be defined if it's not defined in Rn or something like that. So we have to understand how to deal with this question. Okay, now the aim is, let us first write down explicitly what is our aim. Let omega be a bounded domain. Okay, with a C1 bound. You know what is this meaning? C1 boundary. Now consider the problem. Minus Laplacian of u is equal to fx in omega, and it is given u equal to g on del omega. This I name the problem P. Let omega be a bounded domain. You know what is the meaning of a bounded domain with a C1 boundary. That means this type of cusp type of thing are not there. Okay, with a C1 boundary. Consider the problem minus Laplacian of u equal to fx and u equal to g on the del omega. Okay, okay. Why? This is your domain. Let's say omega. So you have to solve the equation Laplacian equal to f inside omega, and at the boundary it satisfies the condition that u equal to, you know that, because from the well-posedness of the problem, you always need a boundary conditions, right? So you want to study this problem. Given omega to be a bounded domain with the C1 boundary, consider problem minus Laplacian equal to fx and u. Because in Rn there is no boundary, so we don't put any boundary condition. That is minus Laplacian of u. This f in Rn. Okay. Now u equal to g on del omega. Now the question is, can we? Last time what we said, that if f is given, F is given, we want to solve minus Laplacian of u equal to fx. So solution is given by phi convolute. Phi is a given, always a fixed function, because you know what is that fixed function. That is the fundamental solution. F is given, so you just convolve with F, you got a solution. Okay. The same question we would like to ask. Can we get an expression for u in terms of f and g, because of course g will also play a role, because there is a boundary condition is given. If there is no boundary condition, only so here this u equal to, if you define u equal to phi convolution f, then I am getting a solution e, a solution, the expression, a expression of a solution which is given by f, expression phi convolution f. The same thing we would like to ask for this case. Can we get an expression for u in terms of f and g? Is the question clear?
Yes, sir.
Others, for others?
Yes.
Yes, sir.
Is it clear? Okay. Now, before doing that, we will see how we will do. But before doing that, recall, can you tell me what is this? Some formula. Okay. Let omega be a bounded domain with C1 boundary, and let UV is a continuous intersection C1 up to omega closure. Okay. Of course, this f and are given to be continuous. That's okay. But recall this. So can you tell me what will be the formula? Laplacian u into v minus Laplacian v into u. This is I'm writing as del omega del u by del u to v minus u into del v by del u d sigma. How to prove this? Anyone? I'm writing this left hand side is equal to right hand side. How I am writing? How I am writing? Yash, how am I writing this?
Like using Stokes or Green theorem.
What theorem? I always say just use so all this theorem, only one theorem you need is that integration by parts. Let's apply here. Please apply, write down. Omega. What is Laplacian? You can write divergent of gradient of u. Similarly, the divergent of this I am writing. Same thing. What is the meaning? Just divergent of gradient. You know what is that. Now use the formula integration by parts here. What I will get here? This I will get is minus omega gradient of u into gradient of v plus the boundary term del omega del u by del nu gradient of u dot nu I will get, right? Dot nu. So del u by del nu into v. Yes or no? This term. Yes or no? By integration by parts. Yes, no.
Yes, sir.
Yes.
Here you again use the integration by parts. The integration is there, so minus omega gradient of v into gradient of u plus del omega del v by del nu into u. So you just take the minus inside, so this will be plus and this will be minus. So this cancels out, so it remains is this, and that is equal to this. Okay, just integration by parts, nothing. So all your Gauss theorem, Stokes theorem, whatever I am calling, it is just a integration by parts. Okay. Okay. So you recall that theorem. So again, because I will be using this theorem always, so I just write down here. Laplacian u v minus Laplacian u is equal to del omega del u v minus u del v by del okay. Now just let. So our aim, you understand our aim. We want to find a solution in terms of f and g. Okay, this is our aim. Let us try. Let us see how we can do. Let phi be the fundamental solution. The fundamental solution. You know what is the meaning of that? Fundamental solution. That for n equal to 2, it is minus 1 by 2 pi log x, and other is a constant Cn mod x to the power 2 minus n. Okay. Fix some x in omega. So this is your omega. Omega means you want to solve this problem, right? This omega. You fix some x here. Okay? Fix some x. Consider the function. Consider the function psi of y is phi of y minus x. Now tell me how this function will look like now, because you know explicitly this is minus 1 by 2 pi mod of y log of mod y minus x, because this is for n equal to 2 and some constant time y minus x 2 minus n for n greater than equal to 3. Yes or no? Yes or no?
Yes.
This is just I have written down a function because omega is a subset of Rn. So for this, just, and where is the singularity of this function phi? Where is the singularity? This function is not defined for
Y equal to x.
y not equal to x. I define this function psi y as y is in omega, and y not equal to x. I define this function psi y, which is nothing but phi translate with x, and x is a fixed point in omega. Okay, so only problem is at x equal to y equal to x. It has a, so all over all point, this function is a well-defined function. Okay, is that clear? Okay. Now our always, so the problem is there in x. So this is a very fundamental trick we will be in every analysis people use, is that the singularity is at x. So what I should do? Anyone? What I should do? First of all,
We
I have to
should
study.
take a ball of radius
Exactly.
epsilon around
Exactly.
x.
The problem is at x. This is a standard trick in harmonic analysis, PDE analysis, function analysis, everywhere. So wherever the problem is, you just take a small epsilon around x. So here this is a domain. Okay. So you define a domain. Let omega star is nothing but omega minus px epsilon. So this is your x. Take out epsilon ball. Okay, good. So if you don't like this is nothing but I just with the drawing. This is nothing. Okay. Now apply this formula. This formula with u and v equal to capital V. So u is some function. U is some function. We will see what is that function, and v with phi. You just apply for this for holds for every u and v in C1 omega closure intersection C2 omega. for every uv. So first of all, we have to see whether, of course, I take u to be a C2, very smooth function up to omega closure. Is phi equal to phi is a C1, C2 function? Yes, because our domain is this omega star outside this. So this is a very smooth function. If x not equal to y, this is a very smooth function. And I have taken epsilon ball out. So in the omega star domain, psi y is a very nice function. Clear? Is that okay? Yes or no?
Yes.
It's a very nice function, phi of y minus x. Now apply this formula here. So what will be that formula? Integration omega star Laplacian uy. This u is any C2 function, omega closure. Okay. We will see later. We will see if you solve that PD, that what will happen. First of all, for any C2 function u and v, in particular, I have only chosen v to be this. Okay. See the magic. U Laplacian of v y minus x. This is nothing but, what are the boundaries of del omega star? What are the boundaries of del omega star? This is the original boundary, del omega, and this boundary. There are two boundaries. So del omega, the original boundary, union del v x epsilon. Okay? Del u by del nu y, phi of y minus x minus u del phi by del nu y minus x. Okay? Okay. Now tell me, what will be this? Your y is here, x is here. What will be Laplacian of y minus x?
Just zero. Was
Exactly.
fundamental solution.
Because Laplacian, what is the fundamental? Laplacian of x equal to 0 for any x in Rn with x not equal to 0. For x not, so here x minus y, just translate it. So Laplacian of px x minus y equal to 0 for any x in Rn with x not equal to y. So of course here the variable is y, x is fixed, same thing. So because that is why this is important, omega star. Otherwise I can't say. You understand? This is equal to 0. So we have omega star Laplacian uy phi of y minus x is equal to, there are two parts, del omega del u by del nu y phi of y minus x minus u del phi by del nu y minus x d sigma y plus del b x epsilon del u. I assume that there is no intersection. Okay, of y phi of y minus x minus u del phi by del nu at the point y minus x d of sigma y. Okay. Okay. At this point, so this we have obtained for any u C2 omega and v with this function. At this point, I assume that u solves p. That is minus Laplacian of u equal to fx in omega and u equal to g on del omega. Assume this. So first of all, you assume that you solve this problem. Okay. Okay. Then what will be? I just multiply with phi in the equation 1 minus Laplacian u at the point y phi of y minus x. I multiply this equation. You solve this equation. Okay. Now I multiply this equation p with phi of y minus x. Okay. So if you solve this equation, then you solve this equation in here also. Yes or no? If you solve the equation minus Laplacian u equal to fx in omega and u equal to g on del omega, then you also solve the equation minus Laplacian of u equal to fx in omega star and u equal to g on del omega star. Yes or no? Yes or no? Huh? Is it true?
Yes.
Huh? No, because you just see omega star is there. Omega star consists of two boundary. Del omega u equal to g. But at del b x epsilon omega, the boundary we don't know u equal to g or not, because this is an interior set. Interior, this del b epsilon is contained in omega, right? So this is not true. Okay, is that clear? Is that clear? Not
Yes.
clear. Clear. Okay. So, but in omega star minus Laplacian of u equal to fx. Clear? That is okay? That is okay? Okay. So if I integrate this, this happens to be Laplacian uy. I just integrated omega star, nothing else. I multiply with this and integrate. Nothing else I have done. Okay. Here I've just used the fact that Laplacian u satisfies this equation in omega star. That's all. That means minus Laplacian u into phi minus 1. Is that clear? Here I have just used that u solves this equation p. That means this implies this. Now you can substitute here. Laplacian u phi of y minus x is nothing but minus of fx phi of y minus x. Is that clear? Is that clear? Which is equal to this one, this part, which is equal to, you know, del omega star del u by del nu at the point y phi of y minus x minus u del phi by del nu y minus x d sigma y. So this equal to minus of this equal to this because of this is okay. Okay. Now taking epsilon tending to 0 in the this side. LHS means here what will happen? This will converge to, anyone, any idea where this function will converge to as epsilon tending to, because omega star is nothing but omega minus b0 epsilon. Where it will converge? Huh? You just use phi is a locally integrable function. Fx is a continuous, so this f is a continuous function. So I forgotten to tell you, f is a continuous function. See up to omega closure. Where this integral will converge as epsilon tending to 0? Huh? This will converge to minus full omega fx p of y minus x by dominated convergence theorem. Okay, by dominated convergence theorem. Okay, you just use that f is a continuous function in omega is a bounded domain. So f is a so omega closure is a compact set. So you just take the supremum out and phi is a L1 integrable function. So what will be your dominating function? Dominating function is a supreme, that the supremum of f into phi. That is your dominating function. Okay. So by DCT this will converge to this. So LHS using DCT just imply that omega star phi p of y minus x will converges to omega fy p of y minus x dy. Clear? Okay. Now let us see what happened to the RHS. So there are two part RHS. So what is this RHS? del omega del u by del nu del phi by del nu d sigma y plus del b x epsilon del u by del nu y phi of y minus x uy del phi by del nu at the point y minus x at the boundary. So as epsilon tending to 0, what will happen to RHS? This is intact. This is intact. There is no epsilon dependent. Now you tell me where this will go. Who will tell me? First term, where the first term will go? As x del b, this will epsilon tending to 0, where this integral will go?
Phi x.
What?
Phi of x.
You remember last class what we have done this? Just think. Not exactly phi of x.
So since phi is a radial function, we can take it out. It is a constant on boundary. So we can take it out like
Yes.
out of the integral.
This converges to 0. Clear? Because phi of y minus will depend on epsilon only. This epsilon comes out. And as epsilon tending to, we will say this del u by del nu is some gradient of u into x by epsilon. We have done this. This will go to 0 as epsilon tending to 0. Okay? Because you can explicitly write what is phi of x. Because it will be phi of mod of y minus x. So this is nothing but phi of epsilon. Because mod of y minus x is nothing but epsilon. Because it is at the boundary of the ball. So phi of epsilon, you write down the epsilon, take it the epsilon out, del u by del nu is the gradient of u into nu. What is the minus y by epsilon is the unit normal. All these epsilons gets cancelled. Gradient of u is a C2 function. So no problem, as epsilon tending to 0, this term will go to 0. Exactly we have done this in the A part or B part in the or last. Where this integral will go? Today only I recall this. Del phi by del nu f of x minus y. Now you just see this integral. Del phi by del nu y minus x into y. This will converges to, this minus is there. Minus this integral. This because this integral means this integral will converge. We have done this. This integral del b del phi by del nu f of x minus y. So clear? Is that clear?
Yes.
Okay. This will converge to ux. So what are we obtain? So we obtain finally we obtain if u solves this equation, u solves no problem, then because just you write down this is minus ux, this is this, RHS is nothing but integral f of what is that, f of y phi of y minus x dy is equal to the boundary term. Okay, what is the boundary term? The boundary term is del phi del u by del nu at y phi of y minus x minus gy, because uy at the boundary is given to be g, right? That is why I have written gy del phi by del nu y minus x d sigma, okay, minus ux. Now rearranging the term, we have rearranged the solution ux. I write down del omega by del nu phi of y minus x minus gy del phi by del nu at the point y minus x d sigma. So we have got a represent. If u satisfies that equation, then I can write ux equal to minus integral fy phi of y minus x dy plus the boundary term del phi gy d phi dt. Is that clear? Huh? Is that clear? But now we want to see g del phi by del, everything is known. Phi is known, del this is known, this is known, because phi is the, you know what is phi. Phi is the fundamental solution. I just all, but the problem is still there. There is one small problem. Can you identify what is that small problem?
We'll need to eliminate del u by del gamma.
Del nu, yes, we have to eliminate, because in the representation formula, this is a problem. This is a problem. Okay, this is the problem, because you have still need to eliminate del u by del nu, because the solution I am writing in terms of del u by del nu. This is nonsense. So still I have to eliminate this. If I can eliminate, then this will be a nice representation formula. How to eliminate this? Now our goal is to eliminate del u by del u. Okay. For that, let us define a function for fixed x, that same x, I define a function. Let phi x solves the problem and x is a fixed number. Subscript, like we write down something, some for each x, fx is a function like that. So you fix x, what is that x? X is the same x. This x. Phi x y equal to 0 for all y in omega, and phi x at the boundary behaves like phi of y minus x. So it's a harmonic function for all y in del omega. So what is phi x? Phi x is a harmonic function in omega. Okay, so interior minus Laplacian of phi x equal to 0. That means it's a harmonic function with some boundary condition. This is, I don't know whether such function exists or not. You just let phi x solve this PD. Suppose you have this type of function. Suppose you have this type of function which is equal to 0, and at the boundary it satisfies phi of y minus x. Okay, now I'll apply this formula, Which formula? This formula. Okay, apply this formula, apply the previous formula. With same u and v equal to this phi x. If you apply this and using the harmonicity of this function, you will obtain is minus omega fy phi xy dy, because you don't have to apply it near x bx epsilon, because inside phi x is a nice function. Okay, now outside you will get del u by del nu at y. See, phi of y minus x minus gy del phi x by del nu d sigma y. Okay, see, this term I have to eliminate, right? I write down, I put it here back in the right hand side, this term. Okay, now substituting this term, substituting, you call it 1, you call it 2. So I can write, see, this term is there, this is term, this term is this, the same term. Okay, now I can eliminate like that. I can write integration del omega del u by del nu phi y minus x is nothing but minus fy phi x plus integral over del omega gy phi x. Okay. Now substituting 2 in 1, we obtain something like that. Ux is nothing but omega f of y phi of y minus x phi xy interior dy minus gy del y del nu phi of y minus x phi x at y. See, so I have introducing this function. I have eliminated that del u by del nu into phi of y minus x term. Okay, but the problematic part here, I have to introduce a new harmonic function which phi is superscript x, which is a harmonic function and satisfies the boundary condition that phi of x equal to phi of y minus x. Okay, clear? But this will have a great implication in our study. Okay, these function, so phi of y minus x minus phi superscript x and phi of y minus x and del u by del nu, I name it some function g of xy. G of xy. Okay, definition. This is the most important part in Laplace equation. Define. It defines this function. This you know. This function is the fundamental solution. This is some harmonic function. Is called for x. This defined for x and y in omega, but x not equal to y. Because x equal to y, you cannot define this function. Okay, x not equal to y is called the green function of the domain. That is why I name it G, because it's called green function. This is called the green function of the domain. That means if you wish to study the solution of a equation minus Laplacian of u equal to f minus Laplacian of u equal to f and u equal to g in omega on del omega. If you know the green function of omega, that is phi of y. This you always know, phi of y minus 1. That means to find a green function, we want to study the function minus left. We want to find this function. This is a harmonic function and phi of xy at the boundary is phi of y. Then you are done. If you want to study the green function or the solution of the PDE minus Laplacian of u equal to f and u equal to g on the bounded domain, we want to compute the green function for the bounded of the domain. Okay, because once you have the green function, you know what is the solution. F of y, this is the solution. Then if u is the solution, then if u has a solution, then you has to look like this. Clear? Is that clear? So now the question is how to compute those Green's function. We will do for some domain how to. This does not depend on the equation. This green function only depend on the domain, right? Because phi of y is you know what is that explicitly you know, but it depends on how to find the harmonic function. So the main idea to obtain a green function is to compute the how to find the green harmonic. Once the harmonic function is done, you got the harmonic function, then you just subtract these two functions and you get the green function of the domain. Now we will see that not always it is easy to define the green, to compute the green function explicitly. But for some of the domain omega, you can compute the green function. Is that clear? Once you know the green function, you can solve the PDE minus Laplacian of u equal to f and u equal to g on the boundary. Okay, that is why the green function, that we call the green function of the domain. You understand? Okay. Now you tell me, is there any question? Huh? Is there any question? Atharva, Yash, Ekans, Vivekan, Kritika, Shivani, Shammi, Vishwa, Navneet, Chitram. Do you understand this?
Also, you cannot.
Haha. I cannot hear you.
But it's also not easy to.
Haha. I cannot hear you. Please. Please.
Hello.
Again. Huh.
Yeah. That it's not easy to find this phi x also for this.
No, no, no. Not always easy this to define the phi x. For some particular domain you can compute, but not always. Okay. Okay. But there is the existence is guaranteed with some other. This is a very deep problem. The existence of green function can be guaranteed that for any domain with a C1 domain or if even ellipsis domain, any smooth domain, there always exists a green function. But how it looks, we don't know. Okay. But we will see that for some of the domain you can compute the green function. And what is the significance of computing the green function? The significance is once you compute the green function, you can write the solutions. Okay? You can write the solution. Is that clear? Is that clear?
Yes.
Okay. Let us.
Sir, is this
Follow.
uniquely determined?
That's a very good question. Not. No. 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 Okay. This is a different question. Okay. Very good question. There is something uniqueness in some class, you can say that it is uniquely determined. Some domain when I will compute, that is uniquely determined. Okay, I will tell you. Not always.
Yes.
Very good question. Theorem. Let, now I write down a theorem. Let U is a C2 omega intersection C1. Just what I have did, I just now write as a theorem, satisfies the problem P, then U is given by okay, clear? Now let us do some properties. Properties of G. First of all, what will be the Laplacian of Gxy? Can anyone tell me? Just think. G of xy is what will be the Laplacian of y for fixed x? What will be this? Anyone? For x not equal to y. What will be the Laplacian?
0, like
Exactly, exactly. You know, for all y in omega
not equal to x.
with yes, it's not equal to y. Okay, this is a not easy problem. This is symmetric function for all xy in omega with x not equal to 1. Okay, this is a triviality. How to prove this? Any idea? This is not easy proof.
It's difference satisfy the like
Yes,
almost
something.
approximation.
Nice. You let define uz is g of xz. So this function is defined in z belongs to omega minus x, right? You define vz as g of yz. Z defined in omega minus y. For epsilon positive, define omega epsilon as omega minus, same trick, bx epsilon union by epsilon. So what is your domain? So you have this domain, right? There is some x not equal to y. So y is this. You take a domain, you take this. This is your z. Okay, this is your omega star. Okay, so this is your omega star. And your uz, you know what is your uz, you know what is your vz. Now apply that famous formula. Okay, the C1 domain, so omega epsilon is a C1 domain with u and v is of course definitely omega epsilon. Closure, right? Apply that formula. Start with u and v. Then what is Laplacian of u in omega star? Who will tell me? Huh? What will happen, man? What will happen? This? Huh? What is Laplacian of u in omega star? And what is Laplacian of v in omega star? Your u is this, v is this. So what will be your Laplacian of u in omega star?
0 from the first property.
0, 0. And again this omega star you write down omega minus boundary of this bound. So this is the boundary, this is the boundary, this is the boundary, this is the boundary. You write down again as omega epsilon tending to 0. What will you get? What will you get if you write down properly? You will get something from here. You will get g of yx. From here you will get, you check, g of xy equal to 0. And this implies same that formula again, that f of x f g of y equal to g of xy. Clear? This is symmetric. You prove the symmetricity of the Green function. Did you get how I get this and this? Huh? Same thing. Remember, this type of term will come. This is your g. This is del g by del nu, right? So it will be g of x, z is there, right? Y, z is there. As epsilon tending to 0, this will converges to g of x, z. Okay. Similarly, for other term, we will be getting g. And other this term is again 0. Similarly, the other term we will get g of y, z. Okay. You just check. You just check. So this is a beautiful property of a Green function, that the Green functions are symmetry and Laplacian of gxy is equal to 0. Okay, good. Now let us compute some example. Okay, and then we will stop. Let us compute some examples. As I said, first, this Green's function is uniquely determined when your omega has some specific structure. Okay, example. You want to compute Green's function for Rn plus upper half space. Xn equal to positive. Oh, well, first of all, can anyone tell me what is the Green function for Rn? What is the Green function? For the way I define it, what should be the Green function in Rn? Just think, what should be the Green function? What should be the Green function in Rn? Your fundamental solution satisfies that all property. Come on. Phi of y minus a, and what is that harmonic function? Any constant is a harmonic function. So that is why I said that Green's function is not always constant, because your fundamental solution minus a constant is also a green function, right? Yes or no? Yes or no?
Yes.
Similarly, okay. So in that way, so fundamental solution, the definition is the fundamental solution is a green function. So sometimes in the literature that is called also the green function for the Rn, or sometimes it is called the fundamental solution. Okay. Because this green function all may not, because the way I define green function, it may not be unique, because any constant plus the fundamental solution is again a green function, right, for Rn. Okay, green function for Rn plus. We want to find a harmonic, so we want to calculate the Rn. Rn plus, you know, this is xn equal to 0. You know what is that, right? This is a plane x1. This plane is xn minus 1 comma 0, and this is x. Okay. We want to find an harmonic function satisfying right? We want to find a harmonic function, then we are done, right? Any idea how to compute? Just think the Rn. This is your xn equal to 0. Your point, you consider any point x, because you know phi of x, y you have to find, right? Phi x, okay? Now define x bar. This is your x bar. What is x bar? Just take the reflection with respect to this plane xn equal to 0. Okay, take the reflection. X bar is nothing but x1, x2, because you just remember you have to find a harmonic function in upper half space. You have to find a harmonic function here. Okay, this is your Rn. This is your x. So this is your, so you consider any point x. You take a reflection with respect to this plane, that xn equal to 0 plane. Okay? Okay? Is that clear? Now I define a function. This is a very beautiful idea. Define a function phi x of y is nothing but phi of y minus x bar. Now you just tell me, is Laplacian phi x equal to 0 for all y in Rn? Plus, yes or no? The idea is you want to find a harmonic function, right? So you cannot use the fundamental solution, right? Because you know fundamental solution is not harmonic except at one point. But you want to find a harmonic function in Rn plus. That means you just take a point x, you just reflect it away from, reflect it with respect to xn. So this x bar is not a point in Rn. This does not belongs to Rn plus. Yes or no? Yes or no?
Yes.
This does not belongs to Rn plus, provided this this x is in, does not belongs to del Rn plus. Okay. Of course, if the point is here, the reflection, that this reflection is this point, right? So if x does not belongs to Rn plus, then x bar always in Rn plus. This does not belongs to Rn plus x bar, right? That means this function has only singularity where the function. So Laplacian of phi is always 0, except when y is not equal to x bar. But our y is in Rn plus and x does not belongs to Rn plus. So for all y, phi x is equal to 0. So you get the idea how to construct such Green's function, this harmonic function. Okay, but still you have to check one thing, that phi x, y has to satisfy phi of y minus x if y is in del Rn plus. Is that true? So clearly, first is checked. Clearly, Laplacian of Vx equal to 0, because Laplacian of Vx means Laplacian of Vy minus x. It will be 0 except y not equal to x bar, and x bar is not in the domain. So no problem. That's done. Now we have to check this, that phi xy is phi of y minus x if y does not be, y belongs to del Rn. Let us check whether it is true or not. Let y is in del Rn plus, that is yn equal to 0. This imply y minus x is equal to y minus x bar. Means you take any y here, you take any y in the boundary, then the distance, this using the reflection property, the distance between y to x bar is equal to, so this distance is always same. This is a property of it, because this is a reflection around xn, so this is always same. Is that clear? This is always same, just using the reflection property. This is always same. Okay, and we know that capital phi is a radial function. Radial function. That means it is phi of, if the distance are same, the value will be same. Clear? And that is we obtain phi x bar of y is equal to phi of y minus x if y is in Rn plus. Is that clear? All of you? All of you?
Yes.
Okay. So this is the way one should think. And now you can ask me why I have think like this. You can think some other way also. I don't know. But this is the most, so means one, so the idea I can tell you when I learned these things, was my idea, is that you have to find a harmonic function, right? So the most easy, so what is the most easiest example to find a harmonic function? Is the so your fundamental solution is almost a harmonic function, right? Except at one point. So you have to somehow remove that point. We have to somehow manipulate that point so that this phi becomes a harmonic function. So the easiest manipulation is you take the point outside the domain and you get and define such function in this way so that this distance is preserved and this becomes a green function for the upper half space. Is that clear? Okay. Now you can explicitly compute the green function in the upper half space. Okay. Because if now you compute, let us compute. That means you can compute gxy is equal to phi of y minus x minus phi of y minus x bar. So this is the green function. Now you can compute what is del g by del yn. If you compute, you will see, because you know what is the value of this, you know what is the value of this, because both are the fundamental solution, just the points are different. You can calculate, it will be del u by del n alpha n yn minus xn y minus x whole to the power n minus yn plus xn y minus x bar whole to the power n del g by del y. Okay, now if your y is in del Rn plus, then del g by del y Rn. For such point y is in Rn means yn equal to 0. Your yn equal to 0, right? You can compute easily that you will get 2xn n into alpha n you can calculate it. N by 2. Okay, del g by del y. Okay. Okay, now just I want to write one more thing. So this is because remember, if I now let u be a harmonic function in Rn. Rn plus with u equal to g on del Rn. So instead of your f is given to be 0. So minus, I have written f, so here f is 0 and u equal to g. How to solve this? U will be a harmonic function satisfies del Rn. Then the representative formula says that ux will be given by minus Rn minus 1 because this is del g by del yn xy gy dy. Clear? Which is, you know what is del y by del n at the boundary, 2xn by n on alpha n. This is Rn minus 1 gy xn square plus dot 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 xn minus 1 minus yn minus 1. This is a n by 2 dy. Clear? Is that clear? I am just writing. So this is, you can compute, right? Del g by del yn is easy to compute because you know what is phi of y minus n. But now if y is in del n, that means y is yn equal to 0, yn equal to 0. You will have, you just simplify this computation, you will get this. Okay. So del g by del yn at y equal to Rn plus is at the boundary is. So suppose I want to study these equations, minus Laplacian of u equal to 0 and u equal to g on the boundary. Then you can write down del g by del yn g by dy because f equal to 0, so these terms go away. First term goes away, right? So only the boundary terms and the inverse. Okay? Just writing, nothing bad. Okay? Because this has some name, that is why I am writing the function. This function, this del g by del yn at the del g by del y is known as this kxy function. In alpha n. This function, okay, is called the Poisson kernel. This has a name. Poisson kernel for Rn plus. Okay, Poisson kernel. This is known as Poisson, and this solution is called Poisson solution. This is a Poisson equation. Poisson equation. Okay, this is called Poisson equation. This is called Poisson equation, and this kernel is because any function is given by this del g by del y xy gy, right? So this is known as the Poisson equation, and this solution, if u is a harmonic function, then u has to be like this, okay? And this kxy, this part, the kernel is nothing. The kernel is this. This is the kxy. The minus of that is the Poisson kernel because minus is there, so minus of this is the Poisson kernel. Okay, is that clear? What is the Poisson kernel? So this is an example where I've computed the green function, that upper half space. Next example 2, I will not do today. Just think about it. Example 2, you want to do it for the ball. Green function for the unit ball. Just think what to do. Any idea? So your ball is this. Any take point, any x. I have to define some x star which is outside x. You understand what I am to do? So, and also that this distance is preserved. This distance is preserved. What to do from the boundary? What to do? Have you seen this function x star for x not equal to 0? Huh? So mod of x, if x is in B01 and x not equal to 0. So then mod of x star is nothing but 1 by mod x. So it is outside the ball. So x star is the mod of x star is 1 by mod x. Mod x is less than 1. So 1 by mod x is greater than 1. So it is outside the ball x star. Okay. Now I have to define this phi of x, y, something of this form with this form. You understand? This is known as the inversion. You have studied this in, I guess, is in complex analysis, inversion. Okay, we will see. So next class, you just think about it, how to compute the green function for the unit bond. Is that clear? So next class we will do. Okay. Next we have to fix the date for the quiz 2. So next week we can fix the date. Atharva, Yash, because it was scheduled to be this week, but this week already some holidays are there and all those things. So can we fix it next week?
Yes, sir.
So from 7 o'clock in the evening, is that okay? All of you? Huh? Because I don't want to miss a class. Like Tuesday evening, 7 o'clock. Is that okay? Yes or no?
It's quite late. Can it be in morning?
But others have a class, no? That maybe the problem is one can have a. So which day? Maybe we can fix it on Wednesday at 5:30 or 4:30 or something. Because Wednesday you don't have a schedule, right? Yes or no? In the late.
Yes, sir.
Okay. Wednesday I will write an email. Wednesday like 4:30 or 4:30. Is that okay? Yes. Others? At least I will send an email. Okay.
Yes.
Okay. The syllabus is, I will write down, the syllabus is for up to today's lecture. Clear? Clear?
Sir, can you
Yes.
also upload some like examples, practical examples that we can solve?
Practical
Not
example?
abstract one.
Which one?
Like-
Where? For green function?
Yes, sir.
I will do that. There are many. I will do that. Okay? ठीक है? Is that okay?
Yes.
Okay. Thank you.